Yeah, thank you. It's a great pleasure to be here. As I said, when I left Seattle, it was frozen this morning. It's very nice to come here and talk about the cloud, although I don't think you see them very often here, right? This is my group. It's called the Sensing and Energy Research Group. We position ourselves at the system research at the boundary of the physical and the computing world. We do things both on the device side. We design embedded devices, sensors, circuits, RF communication for interfacing with the physical world. We deal with managing physical data and mine them to extract useful information, and also deliver all the way to the application level to achieve either energy efficiency, and in the most recent times, I've been doing context awareness services for mobile and cloud computing. Just give you some sense of the artifact, the things we've built and things we've shipped in some of the Microsoft products. We did a bunch of these low-level sensors. Lots of them leverage the RF properties as well as the cloud computing power. And we did an architecture for low-power continuous sensing for the phones. That's pretty much become the standard if you use your multi-core phones today. And we did a bunch of work in the data center field that I'm going to talk about more in today's talk. And shipped our technologies in Visual Studio, in Windows Phone, Windows, Bing, and so on. Data centers, as I said, many of you probably haven't been to a real mega data center. You can see the size of the sheer scale of this thing compared to a sort of single-family house or the cars on the street. These are gigantic infrastructure this is a water chiller, this is a bunch of air handling, the shipping dock, and it just take a lot of effort and money to build. Ever since 2006, I think, about 10 years ago, there's a lot of attention paid from the government and the consumers and the industry on the energy expenditure of cloud computing. Or back then, it's more called data centers than cloud computing infrastructure. And if you summarize them, the industry is really on fire. People are talking about, as an industry, we're consuming about 2% of the U.S. Total energy production. It's enough to power 5.8 million average U.S. household. It doubles every 5 years. It's just become something that not sustainable. So there's a lot of environmental and energy efficiency attention got put on this. But if you look at people who actually build and operate data centers, right, 2% of the energy is a big number, but it may not be the bread and butter and the cost of people who actually run it. And what exactly motivate the cloud providers so much to care about energy is really the money behind it. Not the money in terms of greenness, but the money we have to pay to build and run these data centers. To give you a sense of the scale, in the Microsoft Chicago data center, which hosts about 200,000 servers, it's 700,000 square feet facility, huge, two floors. You can just read the numbers, the number of tons of coppers, the power cables we have to lay down, the structure strength, the concrete, the conduit, and everything. And this is about providing 60 million megawatt of critical power. That's the power that you give to the servers. And in order to support the cooling and everything, the whole infrastructure is more than 100 megawatt power capacity. What does it mean converted to dollars? It yearly costs $10 per watt to build a data center, including servers. So for that facility, we're really talking about more than $500 million to build the data center. And if you look at the cost that actually goes into own a server to run it in the cloud, the biggest part of the pie is still the server cost. right? You have to buy the server, which is almost half of the cost if you amortize the server for a 5-year lifetime and amortize the infrastructure for 15 years. The actual amount of energy you use to run the server for 5 years it's okay size of the pie. It's about 20%. And that part is growing because the energy price is going up. But what's related to that is the whole infrastructure you have to build. The amount of the capacity of the cables, the electrical and the cooling and everything else that goes, that have to scale with the power, not necessarily the energy, that to host these servers. And then it's 12% of the people and the networking and those costs goes there. So if you add this power-related size of the pie, it's quite significant. It's almost as big as the amount of money you pay for buying the servers. And this is going up as the energy price going up and the hardware cost is going down. So what is in the data center that make them so expensive to build? Very intuitively, we see, well, data center has servers, has networking, and connects to the internet. That's the functional part. That's what people would normally think about what a data center would do. There's the entire power infrastructure. You get power from the grid, conditioning it, convert it to different voltage, UPS system in there, and distribute it to all these servers. The grid is not that reliable. This is the number of, this is in production Microsoft data center, the data we collected, the number of power outage on a year, over a year, 1 to 2, 3, up to 7, sometimes even more, and the duration of the power outage. So UPS is not enough. Some of the power outage actually lasts for quite long. And so you have a backup generator system that's typically gasoline powered. There are different ways of doing that. And of course, the cooling infrastructure. In order to be able to pack these servers at that density, typical data centers use air cool, and air is chilled by the water chillers. So all these infrastructure constitute to that 20% of the total cost that you have to build this to host the number of servers you want to put in there. And the way that people calculate in terms of operation, how efficient a data center runs, is to take the energy consumption of the entire facility and divide it by the amount of energy they actually consumed by the working force, the servers and the networking gears over there. When we first looked at this problem about 10 years ago, I'll just first talk about the servers. Servers themselves are not light bulbs, not like when you turn it on, you always stay at the constant power consumption. It actually varies depending on its workload. And one of the biggest stare there is from just turning on the server without putting any workload on it, you consume about 60% of the peak power there. And then it's pretty much a linear scale of the CPU utilization. So this is, the industry has paid a lot of attention to scale this down. I think the number here right now is a little better, but not that much better. Once you turn the server on, more than half of the power consumption is already there. So you don't want to keep the server idle and not running anything. There's also temporal and spatial relations or correlations among these servers. Right? These are tasks that usually takes a huge number of servers to run. For example, this is this is back in when Microsoft still have messengers, MSN Messenger. This is the number of login requests over a week. You see these patterns. During the day, there are more, and during the night, there are less. And that converts to the power consumption for any server that try to serve these things. You also see this natural variation of the power goes up and down. There's spatial correlations that when, say, one login request or one Bing request comes in, it actually fires up a lot of servers. So the utilization of these servers actually correlate to each other over space and time. And that implies the heat that's generated by these servers actually varies over space. So this is the thermal imaging of the front side of a row of servers. These are vertical ones are server racks. The blue colors are this cold air coming from the bottom in front of the server and got sucked in through the servers. Obviously, this part you don't get enough cooling, and this part is pretty much overcooled. So there are variations of these, and traditional data centers are operating in a very conservative way. And they will say, okay, I don't want any of these variations to trigger any fault, so I'm going to overcool it. I'm going to provide enough power infrastructure, so whatever the server wants to run these will consume, we're going to supply all those power. And that's the cause of inefficiency. So if we look at the amount of power that comes in, the energy the power that comes in from the grid, and how that energy is spent. Each of these is a stair, and that blue part is what's left, right? Cooling, this is assuming a PUE of 2.0. This is saying half of the energy is spent in the infrastructure and only half goes to the server racks. Right? Back 10 years ago, this is very much the standard, industrial standard of how these data centers run. 1/3 of that energy that comes into the data center was spent in cooling. This is just the chill waters and the air conditioning in the room. And then the lighting, the UPS losses, the fan that blows the air into the room, the power supply that the server power supply, if you're not well designed, they actually lost a lot of power. The application may not be designed very well, so the utilization of these servers can be low, because you see those valleys. At the end, about 3% of energy, at least according to that book's analysis, only 3% of energy is spent on useful work. Everything else is to support that. Right? Quite astonishing numbers if you look at it. There are some of the big steps, right? The cooling, the air handling, the power supply, and the utilization. Those are the places we start to look first to try to optimize, try to understand what's going on, and try to help the data center operation teams to operate better. How can we operate better? So the strategy, you can pretty much account them into 3 categories. One is the reduction. You just try to reduce the energy consumption as much as possible. By reducing them, then you can, with the same infrastructure, you can host more servers. 2, you can reuse them. Virtualization and consolidation is one form of that. You put more workload into the same hardware so you can do more. And a lot of people are also paying attention to renewable energies, right? Whether you use solar or wind, they have their own challenges that they're not constant power supplies, and they vary, so you have to handle these variations of sometimes you have extra supply, sometimes you have less, which actually introduces more complexity in the infrastructure. So it's actually a holistic thing you have to think through. So this talk, I'm going to primarily talk about the reducing the energy consumption and encouraging reuse through virtualization and dynamic provisioning. For energy reduction, typical tactics, what you can do is, first of all, you do more energy efficient design by just eliminating the inefficiencies in the system, including both the circuit, use more energy efficient components, and better air handling, and more different size of the rooms and so on. Energy proportionality, I talk about the stair of power consumption when you just turn on the server. If you can make that small, then the energy you consume is proportional to the workload you have to perform. Relax your operation conditions. Don't overcool the data center. Just run them at sufficient conditions. Consolidation, if you can combine, if you can combine the workload to a same hardware infrastructure, you can host more jobs in the existing physical infrastructure. And one extreme one is called oversubscription. This is to say I'm going to pack more stuff into my infrastructure, given the risk that at the worst case, they're going to blow my data center up. But I'm going to control and mitigate that. But by doing so, I would be able to even get more done with the same physical infrastructure. So the approach we took was really a data-driven approach. We start with sensing to measure what's going on in terms of power, in terms of performance, environmental conditions, to model them and use the model, use the understanding to do provisioning and planning, dynamic control, and in longer term to design new forms of data centers. So over the years, we've been doing a lot of sensing work related to data centers, locations, where the servers are, what exactly they do, heat distribution, wiring of both electrical cables and network cables. Turns out if you have that kind of infrastructure, people do plug things in wrong places. As error prone, just which circuit they're on and which network port they're on. Airflow, power consumptions, server type, utilization, weather conditions, and availability of electricity, and so on. Those are all parameters you can use to understand the activities in the data center, how efficient they are, and to optimize. From data to decisions. Once we get all this data, we understand it, and to actually provide feedback and advice to the operation teams. I'll talk about the three things, the easy part, harder things, and really something really ugly, hard to deal with. The easy things are really eyeballing. You just give this to the people who operate it. They will understand, oh, this is something wrong here, and they will try to adjust things to fix it. Or statistics, you can tell them, this is where you are today, this is where you wanted to go, and you'd be able to quantify how well they do, and they can improve from that. I'll use a couple of cases. Case study. This is, in one of the early days, they tried to improve cooling by putting vinyl curtains around the either the hot aisle or the cold aisle. This in particular case, they're putting it around the hot aisle. Around the cold aisle. They say, okay, the air comes from the floor. If they're just open floor, the air will go everywhere. And if I put curtains on, then at least I'm going to constrain the air to be within, to all supply to my servers, and we're not wasting the cold air. This is what we will see when we have sensors in it. This is before they put the curtain on. The top of the rack is the hottest, expected that the hot air can't reach them. So this is a good reason that you want to put the curtain on. The bottom and the middle are well cooled. After they put it in, the overall temperature all dropped, which is a good sign that these things are effective. But the bottom of the rack now become the hottest. Right? The top is cooled better, and the middle is still very cool. They were surprised. Actually, at the time after they put it on, several of the thermal alarm comes up, and they all come from the bottom servers. And it was sort of counterintuitive. They improved the cold air flow, but they're not helping me. The reason is this the so-called the backflow. This is the hot air from the back of the server. When you improve the speed of the cold air flow, there's a so-called the Bernoulli effect. It actually creates a low pressure point here, suck the hot air from the back to the front. And from these points, you basically don't receive any cold air. The normal way that what people do when they see thermal alarm, they increase the airflow. And that's just the opposite thing you want to do here. The faster air you supply here, the more hot air to suck to the front, and the worse it takes. And these kind of just give them the data, help them to analyze this, actually make them accustomed to make the right decision to actually slow down the airflow, and all these thermal alarms goes away. So in terms of just another eyeballing, ASHRAE, which is the cooling organization, used to give very stringent data center operation conditions. This is between 20 to 25 degrees C, and between I think this is the humidity of 30 to 50%. right? That's the relative humidity. That's a very small bounding box. And in order to relax the cooling requirement, we specify, or Microsoft specify this huge box and say everything within there should be okay, because we have computers operating in normal air and everything works. But how to get there? So these, again, data will show them, okay, where you are just in the scatter plot today, and once you do some adjustment, how things are improving. Power provisioning is another interesting case. So when you buy a server, they come up with a peak power. So this server consumes 350 watts. That's the label power that the, say, HP cellular server, they'll put that on. But that will be never reached, right? HP is very conservative in terms of labeling that power consumption. And if you add, just exercise it, exercise all the components in there. There are these benchmarking tools that allow you to do it. You'll come up with a number that's much smaller. You can allocate your servers. You have a 10 kilowatt circuit. You can compute that and use that to allocate how many servers you want to put on the rack. But that's very conservative. You're basically leaving all these available power not consumed. And people call this stranded power. By actually measuring them, you can have a much lower cap and put more servers in on the same circuit. The actual power consumption could be varying, but you can still take a very conservative view of that and say, okay, even with this, using this power number to allocate my servers, I'm going to still be safe. These are all very sort of simple, intuitive things you can do. And through these data-driven analysis and many other work that goes into designing new generations of data centers, over the course of about 10 years, Microsoft had 4 generations of data center designs, and you can see the PUE number, the utilization of power, is getting much and much better when they have smaller size, more modular designs, less air to be handled, and less infrastructure to be built around them. So those are the easy part, right? Just get the number, look at the statistics, look at the plots. You can make relatively good decisions. The hard part, that actually requires some modeling, some control, some dynamic decision making, and so on. I'll use a couple of examples. We'll talk about provisioning servers on the circuit. Actually, if you just provision like we said so, you're still leaving all this white space wasted, right? Nobody is using that power there, but you cannot use it for host more servers. What people would do, so-called the over subscription, is to say, I'm going to take the risk. I'm going to assume all the servers take that amount of power consumption. So I'm going to put more servers on the circuit, with the danger that when the server actually goes on top of the safety line, I'm going to cap them. The typical capping is a hardware activity. It would just specify this server can only consume 250 watts, although it's capable of getting to 280. When it reaches 250, the CPU will be scaled down, the frequency will be lower, the voltage will be dropped, and the power consumption will go down. On the downside, you're going to hurt the performance, but you're going to pay the risk because that allows you to use the infrastructure better. The other case is the so-called power tracking. This is, in typical case, it happens when, let's say the power, you lost power, the data center lost power, you use the UPS, and they use the backup generator. When the power comes back on, you both have to run the normal service. At the same time, have to charge the UPS. So you're going to have a UPS charging curve that initially will require extra power to charge the UPS, and gradually that will taper down. And at that period of time, you actually can't supply all the powers the server need to the compute infrastructure. So you have to do more aggressive power capping just to get it gradually to come up. So that's power capping. Another notion is dynamic provisioning. So if we talk about the utilization of these servers goes up and down due to the request. And this is a study we did with connection servers in Messenger. when the load goes up and down, you don't want to turn all the servers on. And you can actually leave some of the server off and keep the ones that's on to keep them busy. I'm going to skip some of the technical details, but basically we were able to predict very well the future load based on the history and the seasonal history in the past. And instead of doing load balancing, which is what everybody would do to run the large number of servers, we do load skewing. So basically, instead of giving this low load server more load and try to bring it to the same level as all the other servers, we're going to give more load to the busy server and keep it hot and drain this guy either naturally or through some mechanism, so that we can eventually turn off that server. For that particular workload we look at, there's several policies, but essentially we can achieve 20 to 30% depending on how much user we would like to kick out because the risk of undercapacity. So that brings the energy benefit. So for those servers, now we can turn them off, and in this case, we're on average going to save maybe up to 30% of the energy. But if you think holistically that you're actually buying these servers, but you leave them there and not using them, why do you want to leave 30% of the servers off, right? So the better way of utilizing that is to put other workload on them, right? This is the why virtualization is getting so popular. So you can leverage the same physical server, run multiple virtual machines on them, and when one virtual machine is not using the resource, the other ones are using it, so you can overall using the infrastructure much more efficiently. But that brings the ugly part of it. So virtualization is a good thing, but it brings a lot of difficulties in terms of operation and control and capping and so on. I'm going to take one example, which we look at deeper, which is the interference between these virtual machines. In particular, the interference because of the shared memory resource. Because of the memory infrastructure architecture of most servers, right? Everything's going through the same memory bus and have a shared cache. If one app, one VM is using some of these cache, it will kick other VM's cache out and going back and forth. We did some measurement, and some other people did similar studies. We saw almost 100% performance slowing down. So by combining two things to the same physical machine. So in this case, instead of putting them all together, you would rather pay the cost and put them on separate machines. And how to characterize it? When you have a cloud service, you're receiving all these tasks coming in. How do you place them to avoid the interference? And we built some tools to quantify and predict the possible interference between VMs. And I'm not going to go into too much details of how this works, but I'll just give you a sense of after getting those predictions, we're able to utilize them to do better consolidation of the VMs to make them be aware of the interference and achieve about 20% total cost of ownership reduction by just placing them better and migrating them. When you have things out of shape because the VM comes and go, we want to remigrate the VMs to pack them better to avoid interference. Another example I want to talk about is the power capping in the virtualized world. That becomes difficult because now if you just cap the physical machine, then you're going to affect every workload that runs on the same machine. But how do you cap an individual VM, and how do you know which one to cap and how much energy they're consuming to begin with? So instead of using physical power sensors, we developed a way to estimate the power consumption based on the VM level resource utilization. So it's a learning-based linear regression of the power, and applied it on top of the performance counters of individual VMs. Some details of to track those performance numbers, and gladly these hypervisors actually provide enough information that we can track them. And using SPEC CPU, this is evaluation, we got about 3% error in terms of tracking these or estimating the power consumption, which is approximately the same of what a typical power sensor would give you. And with that, we'll be able to both account the power consumptions of these VMs and use it for power capping if we need to. So in order to do power capping, we first want to understand how much of a spike a VM can create and how fast can it be. Because if I'm going to talk a little bit later that there's actually, if you do software-based power capping, instead of relying on the motherboard circuit hardware level to do it, you're going to introduce more delays. And this delay has to be compensated. And if the power rises very fast, there's not enough capacitance on the server, then the software reaction may not be fast enough. So on some of these servers, we did some measurement. The fastest observed power range is within like 100 millisecond, 200 millisecond time scale. And on the other hand, there's a lot of correlations when these things, if you're not allocate them carefully, you're going to cause this correlated effect, right? All the servers will spike at the same time. So you have to account for like everything is spiking up at the same time. So the delays of these software-based approaches, there's several steps in reacting to it. If the circuit level observed there is danger of approaching a power cap, it will send it through the network and the agent receiving it and tell the OS, and OS react to it and so on. So we are looking at about 400 milliseconds. It's relatively slow, much slow reaction time than a hardware-based approach. And also for each VM, you can only get probably 10 watt, 20 watt kind of actuation scale. So ideally, you want to take multiple steps, right, to have it converge to get it to the number you want. Luckily, the typical circuit breaker actually tolerates some degree of spikes. So this is a typical reaction of magnetic-based circuit breaker. You can say if I'm going twice as the specified current level, I still have few seconds, in order of 10, 20 seconds to react to it. So 40 milliseconds, and if I divide it by 10 seconds, I can still have several iterations. I can have the controller to talk to the agent back and forth to take several turns to have it converge. So we designed this architecture that allow the data center to do power capping all the way to the VM level with the data center level power controller, the application level, and all the way down to the VMs on individual servers. And by tweaking the voltage and frequency scaling and utilization of these VMs, we can at the end react to the data center level request. Not reacting. So we did some experiments with 40 VMs on 10 servers, give them 3 levels of priorities, and we want to cap the ones that has lowest priority. And with different control mechanisms, you can see without capping, this is the blue one. We actually get significant above a UPS charging curve we have. And the yellow one is the ones that what the control algorithm will give you. So just to recap what we've discussed so far. We've say, okay, when the energy comes into a data center, a lot of them got lost in cooling, in air handling, supply, underutilization. So we want to do virtualization, want to better data center design, better operation, remove the cooling as much as possible, relax the conditions. So there are lots of good things you can do to actually reduce this. One of the things we didn't show you here, and if you look at the complete picture, this is where energy really goes. Right? When you have a fossil fuel energy consumption, this is your power plant. Your power plant itself is not very efficient. You get about up to two-thirds of the energy in the fossil fuel lost in the power plant, and 10% lost in the transmission line that goes to your data center. Right? What we're optimizing from just the energy efficiency and the grid point of view are really a tiny piece of it. Right? So what can we do? What can we do even further to make the IT industry more energy friendly and sustainable? In particular approach, we look at our fuel cells. So fuel cells are, how many people here knows about fuel cells? Oh, good. More than I don't know, right? Fuel cells are these electrochemical processes without a turbine that, or any moving parts that will convert the energy in the natural gas or hydrogen into DC electricity. And I've ride in this Toyota fuel cell vehicle. It feels really nice. So Toyota's, I heard they're going to sell these fuel cell vehicles in United States in a couple of years. And their biggest market so far has been this micro CHP. These are the combined heating and power supply for places that you don't have energy supplies. And eBay and some other data center companies start to use fuel cells to power their data centers. But they're using it primarily as an external power source. Right? As I said, fuel cell is this electrochemical process. Has several advantages. One is the natural gas price on an energy equivalent basis has been cheaper than electricity. Well, you can imagine, right? You're not going through that whole process of generating electricity. And the natural gas grid is actually about 100 times more reliable than electrical grid. Because most of the electrical grid is outside. If you have a bad weather condition and storm, you're going to disturb it. And electrical grid, when you disturb it, right, you lost power for an entire region. For natural gas, they're typically underground. They're buried. They're not affected by severe weather. And when you have a leaking or something, it actually just drop the pressure. It doesn't stop it completely. So the failure is much more graceful. And they're actually easier to store. If you have a data center and need backup energy, you can easily get a natural gas tank than the gas turbines, energy generators that they have to do in a traditional way. They're green too. So if you pay attention to the news, this is earlier this last week, that Microsoft built a data center on top of a wastewater treatment facility that generate methane. This is the waste gas that will otherwise release to the atmosphere and cause a green gas effect. But after collecting them and feed them through fuel cells, Microsoft actually run a data center on that garbage site. It can also be cost effective. This is what we came in and say, okay, with all those good properties of fuel cells, now you can take that traditional infrastructure of a data center, replace all the transformers and UPS and power distribution with fuel cells directly in the rack. So this is actually one test bed we built in UC Irvine, not very far from here. They have a National Fuel Cell Research Center. This is a 10 kilowatt fuel cell that we put together with a bunch of servers. So we can generate energy directly in the rack. By doing so, the data center will have no copper. We have just gas pipes that feeds from the gas grid to these servers directly. So we save on electrical distribution, which is the major part of the cost of building data centers. We don't need backup generators, no centralized UPS, and we measured with a hydrogen fuel cell 53% efficiency. We're now looking at natural gas fuel cells, which going to be even more efficient than this. Right? With that, we did the calculation that we can build data centers about 40% cheaper without having all these infrastructures. It will scale a lot easier because it's just connecting pipes. And then the energy costs, we're going to also save about 40% of the energy if compared to buying them from the grid. So there's a lot of benefits of just using fuel cells and rethinking and redesign data centers. There's also technical challenges. Fuel cells are not very friendly to servers. So these are things that it's a slow chemical process, and they tend to produce a very constant supply of power. And servers are these things that goes up and down. So we need to provision and manage the fuel cells to tolerate these up and downs. So this particular example, we look at the power traces of turning off the power and of a server and turning it back on. And the reactions, this is turning, I think, 3 servers together at the same time. The reaction is the voltage of the fuel cell would drop, the current, this is turning it on, right? The current goes up, and the total power production goes up, but it's actually quite slow. One nice news is actually server crash and all those uncontrollable events doesn't create these power glitches. So these are controllable. These are something that we can plan. We can say, turn this server off, turn that on. So something we can know. So we can use that information to prepare the fuel cells to react to those. So now we're designing a server power supply or a rack level server power supply that takes the fuel cells, provides some local energy storage, and supply the power to a rack of fuel cells. So when there's a huge request of power, the fuel cell will go slowly, try to catch it up. The battery or supercap in the middle can provide this gap of energy and also recharge itself when there's actual productions from the fuel cells. So a lot of new questions under this infrastructure. How do you provision? How many servers you want to put on this site that the fuel cell can supply? What's the energy storage here? Batteries, supercap, different type and size, right? The less you put there, the less capital costs you're going to use. Power capping, again, right? When this is happening, or the correlated utilization happening, and the fuel cell cannot catch up, do you need to cap on this side or coordinate on this side such that to make the total power consumption of a rack of servers to be fuel cell friendly? So we're looking at some of those issues, both from the hardware design and provisioning point of view, and scheduling of the workload and reboot activity point of view. So just to conclude, right, data center are these gigantic large infrastructures. They can take megawatts, hundreds of megawatts to run, and it's also a very rich research space. I primarily focus on the infrastructure optimization and control side. There's a lot of work on operating system coordination, virtualization, performance isolation, tons of interesting work to do. Energy efficiency should not be considered in isolation. Right? This is total cost of ownership. Energy is a piece of it. The facility construction cost and operation cost is all big piece of the pie. Virtualization is a good thing, but it also complicates modeling and control. The industry have done lots of low-hanging fruits, right? We are optimizing the design of it, the operation, but it's actually craving for a lot more new technologies in this space. Going to acknowledge some of our collaborators and coworkers and interns and faculty members who worked on this project for the last 8 years. And with that, thank you and take questions.
Could you comment on the type of fuel cells you're considering for this? Are you looking at like solid oxide for baseload power generation and PEM for the ones integrated within the servers?
Right. We are looking at solid oxide primarily because hydrogen is a lot harder to handle at that scale than natural gas. The material for the pipes and it's all different. But on the other hand, SFC runs at much higher temperature and it's a lot slower to even follow the plots I show are all from PEM. And we just got a couple of SFC and we're installing that while we're talking in Irvine and doing the actual experiments. We see a lot of, I'm not a fuel cell person, we see a lot of new development and new technologies coming up. One of the challenges, in fact, is the protection capability. So we did this calculation. If Microsoft want to build a data center that would talk about 100 megawatt data center, actually bigger than 10 years of production that fuel cell industry can produce. So we cannot get enough fuel cells to even run that. So it is a chicken egg, right? The more demand will make the fuel cell themselves cheaper and the production better, but we don't have that.
So first, of course, this is awesome. And second, the question that I now have, kind of looking at these graphs of where you lose how much power. So you talked a lot about these optimizations that you can do on the servers or in the caches of the processors and so on. But with these fuel cells and pretty much eliminating lots of the transmission losses, in your opinion, which is probably the 2 or 3 most important changes to power consumption that you've developed in this project, but that have the biggest impact on power?
Right. I think it depends on from what angle you're looking at, right? If your power consumption of power supply of the data center is from fossil fuel, then it makes a lot of sense. If you are doing hydro, for example, you're not burning fossil fuel, right? It makes a lot of sense to just run electricity. And you still want to optimize it, right? You don't want to leave the efficiency on the table if they're so easy to do. And I didn't put into this analysis the green energy, right? The solar and the wind. And they tend to come with huge spikes and very unpredictable. And how to handle that is still, I think it's still open question. Right? Handle that efficiently, right? You can put a huge UPS in the data center, but that's not going to be cost effective.
So generating fuel cells for the data center isn't feasible in a decade. And what about just coupling it with a small conventional power generator, coal or gas or a nuclear reactor, 500 megawatts? That would still limit your transmission costs.
Right. Yeah, I think co-locating the power production and data center makes a lot of sense. In the following sense, it's a lot cheaper to lay optical cables than power cables. Fiber is much cheaper than copper. And if you have an energy source and you have the compute demand as one way of consuming it, assume you have lots of demand on the cloud side, it's a lot more efficient to actually move the compute right next to the production. Right? This is true for big ones and small ones and so on. So we've talked to energy producers who are thinking exactly that way. But I think the challenge there is still the majority cost of building and running a data center comes from the server. So you want to use them all the time at high utilization. And if the power source is not very reliable or constant, then you're going to leave some servers idle and not used. And that's the waste in the capital investment. So it's still not there yet. If the server cost is close to zero, then it makes a lot of sense. Wherever you have energy, I'll just put the servers there and use them. Actually, we had a work a few years ago, I didn't talk about in here, called data furnace, which is saying server generate heat. These are low quality heat. You can't really generate electricity out of them, but they're perfect for heating your house or heating your hot water at hospital and so on. So why not turn every furnace into a rack of server? Right? So assuming servers are cheap. But when you do the calculation that you have to buy these servers and the security and putting them in your house and everything, it starts to fall apart. Right? From the energy point of view, it makes perfect sense, but not from the total cost of ownership point of view.
Okay, we'll have 1, 2, and 3. I get to ask the last one. 1, 2, 3, 4. That's it.
Microsoft recently introduced a very interesting carbon accounting scheme throughout the organization. Can you comment on how that influences the design and operation of your servers, of your data centers, in terms of especially the balance between carbon emissions and energy, which is not always one-to-one?
I'm not sure I know the exact details. I know the program. I actually don't know how the accounting was done. I know part of the thing is about accounting the power consumption at the server level. I think they're not at the VM level yet. Of the product groups who are using these servers, right? They counted for how much energy that particular service is using, and then I believe it also counted for the locations of the data center. So some data centers are hydro powered, some are grid powered, so it accounts for the energy source of that, both the cost of the energy when we buy it and also the nature of that energy. So that's how much I know, but I don't know exactly how they come up with the formula.
Between the cooling and the pump usage of energy, let's say it's 40%, so 30% down on cooling and then 10% for fans, but let's say 40% altogether. And then the other number that kind of came out of me from the graphs is that Microsoft currently has this power ratio between the total energy use and the energy use just the servers of 105 to 120.
Right.
And so is it that you have decreased the cooling aspect
Yeah.
so much?
So for those cases, it's complete outside air cooled. So no cooling, chill water, cooling infrastructure, and they're modular designed. They're relatively small, and you just need the fan to pull the air in.
Is there any downside to that?
The downside,
Everybody do that.
right? So there's the climate control is a challenge, and I've heard, I haven't seen it personally. We got rusted connectors, right? So if you have too much humidity in the outside air, not removed effectively, you're going to cause the rusty of the equipment. The other thing I've heard, actually Intel runs some data center in Oregon, is the quality of the air. They have so much grass pollen in the air. They have to replace the filter every week. Right? That becomes sort of a burden to use outside air cool. So I think it's a sort of location dependent thing.
Yes, one thing, this is great, but one thing we didn't talk about is whether there's any hope for the application to optimize its usage based on power consumption. That's how we deal with scale in cloud computing. You do eventual consistency, which is hard to program, but get you around a scaling problem. It seems like you could do the same thing here, which
Right.
is not try to hide the power consumption from the VM or the application. Can you talk a little bit about?
Right. I think the biggest challenge is the interface in between. Neither side know what's happening on the other side. There's the it would be a lot nice if the power capping or the power supply side tell the OS this is what's the available power in the next few seconds even, right? The OS can react to it. Or on the other way around, if the OS can expose to the power management system and say, this is my task and these are the priorities, and if you want to queue, this is how much you can get. A lot of opportunities. I definitely see if we have that pipe there, a lot more optimization we can do.
I got that last question. So now we see the data center being, next generation is going to have prefabricated data centers. So you have a rack where you have separated CPU processing, memory, and everything. Do you think that will change the energy, whatever, profiling or methodology you have here, or it's going to remain the same in these new architectures?
That's a very good question. And there's several advantages by separating that, because on the thermal management point of view, because different components have different requirements. The CPU can sustain much higher temperature than the hard drive, right? You should be able to cool them differently or put them in different environmental boundaries, and the energy accounting become interesting, but I don't think is infeasible. Right? As long as you can trace the activity through, or even statistically, you can say how much is of the CPU goes to application one, and how much the storage goes to the next. By and large, most of the dynamic power come from the CPU. Disks themselves, once they are powered on, they're spinning. You got probably 20% of extra dynamics. So this doesn't contribute to the dynamic part. They contribute a lot to the bottom line, the DC part, right? So if you do accounting in a first order approximation, CPUization is actually a pretty good approximation.
All right. Thank you very much.
Thank you.